Okay, madam.
Yes, sir. Shall we start the session?
Yes, madam. Yes, madam. Please.
Sir, Ravinder Reddy, sir. Shall we start the session? Sir, Ravinder Reddy, sir.
Yes, madam. Yes, madam.
Yes. Okay, sir. I'll just take the privilege of introducing you and the topic. So, good afternoon, all the parts. Good evening, all the participants. We are at the evening edge of the day. So, we are going to have a hands-on session by Dr. R. Ravinder Reddy, Associate Professor, Department of CSE, CBIT, and Dr. P. Suresh, Assistant Professor, Department of Math, CBIT. I take the privilege of introducing Dr. Ravinder Reddy to the participants. Sir has 16 years of teaching experience and has published over 36 research papers in journals of high repute. He has guided 11 PG scholars and is a recognized research supervisor by University of Osmania. As a facilitator for the learning process, he has organized many FDPs, SDPs, and workshops and has delivered 15 keynote and invited talks. He is the principal investigator for 3 research and 1 consultancy project. He was the recipient of Best Teacher Award in CBIT in the year 2018. Dr. Reddy is very active in professional societies and is a life member of IST and CSI. Hope we will be enriching our experience of this knowledge by your hands-on session, which will be delivered by you, sir, and we'll be learning and exploring the domains of quantum computing. Please start your lecture.
Yeah, thank you, madam. Thank you. Yeah, good evening, one and all. So today I'm going to discuss about the quantum concepts, especially in the hands-on. So for this particular session, we required just wait fonts. Uh-huh. Just yeah, I'm increasing the font size. Just wait. Yeah. Okay. So in this session, I'm going to introduce you about the uh, a hands-on session regarding the how we are going to represent this qubits and single qubit, multiple qubits, and with these qubits, how we are going to formulate the circuits. Right after that, we'll see the Josh algorithm. So step by step, we are going to solve. So for doing these things, we need the Jupyter notebook. So in the Python, I think how many of you are familiar with Python? So if you are not familiar with Python, just we have the Python is there. You can type in the Python in the Google, you will get the Python version, or directly you can go to the Google and you type the Jupyter notebook and install this Jupyter notebook. So once you installed and you open this Jupyter notebook, it will be looks like this. Just yeah. So it will be looks like this. So in the Jupyter notebook, directly the beauty of this Jupyter notebook. So can I? How many of you are familiar with Python? Anyone is familiar with Python? Okay.
Participants can.
Okay. Okay. No problem. No issue. So in the Jupyter, in the Python, we have the Jupyter notebook is there. So just the thing is, you install the Jupyter notebook. It's a very simple in the Google. Just you type Python or Jupyter notebook. Simply you can install it. It's not the big task. So after installing this Jupyter notebook or Python, so we need the one package for the quantum computing to solve the quantum computing. So Python is a very rich collection of libraries are available. So this rich collection of libraries will provide the interface for us to do the so many functionalities. So for that we have the for quantum computing purpose we have the QSKIT. QSKIT is there, and another one is the Pyquill is there. Pyquill is the other library. So these two libraries we can use.
Okay.
Yeah.
So can you repeat it? One is QC, and
Yeah,
another.
yeah. I will type down here. Yeah, equal. So are you able to see this?
Yes, sir.
Yeah, yeah, yeah. So these are the two libraries are available in the Python. So with these interfaces or with these libraries directly, we can create this qubit, and we can perform the operations. So in the generally, I think all you are aware that. So suppose if I am taking a is equal to 2, this for the decimal numbers, suppose b is equal to 3, the beauty of the Python is simply just I am showing here, c is equal to a plus b. You can type like this. And just you can print the value of c. Suppose you want to print. So you need not worry. So it's not like the C or Java syntax. Just you can run, you will get the output. So this is the sample just I am showing. So whatever you want to write in the print, you can write. So this is for the normal operations we are doing. But when it comes to the quantum computing, it is different. So here the thing is, suppose if I am representing a is equal to 2 means it is 2 itself. B is equal to 3 means the value is constant. It is we are representing the 3. But in the qubit, the representation is different. The qubit value is based on the state is going to be changed. Whether the in the one place we are going to store either 0 or 1, the values are going to change. So I think all you are know aware of all these fundamentals in the past 4 days, right? I think I need not to stress. I think need not to represent more about that particular one. And this is the basically we perform on the decimal operations. Suppose when comes to the suppose I want to do some operations. So simply I have taken operations for performing in the binary format. In the binary format mean, so generally the computer is going to be represents or performing the data. All operations in the computer is performed on the binary only, ones and zero format. Suppose if I am taking a is equal to 60, b is equal to 13, and if I am performing c is equal to a and b and operation, the first a and b is converting binary and it's performing the result you will get in the integer, and you are going to store in the integer. The result is going to be printed here. This is a binary format. So binary every all, I think all you know. So this is the, so if it is a is equal to 0 and b is equal to 1, true or false, or 0 and 1. So if the value is 0 means itself is the 0, 1 means 1 only. If x is equal to 0, I represent x value is 0. Y is equal to 1 means 1 only we are going to represent. But when comes to, yeah, yeah, I will first I will discuss brief things, then we'll go to the uh, Jupyter notebook. Right, in this hands-on session, so I think all you aware about this decimal representation, decimal data, how we are going to represent, and binary data, the number position we are going to be representing. But these are the basic operations. By seeing this, I think all we are aware that okay, this is the, because as a human being we learn from the school days onwards. Okay, by seeing this we need to add subtraction and division. But in the computer, how it is performing, it is a different addition operation. Means in the binary, it is doing in the different format. Just for the sake of how the machine and human are different perception when while we are adding. And now for the quantum computing, this is a different perception. For the quantum process, the perception now it is going to be changed. So as the human, in the decimal, the plus means what we are doing, and now here it is 1 plus 1, it is 0, we are representing with carry 1, right? So suddenly all we, oh, why 1 plus 1 is, simply we say it is a, in the human perception we say it is 2, but in the binary perception it is the different in the computer, right? So like this, the we have the bit versus qubit. In the classical representation, I say that if the value x is represented 0 means 0, if represented 1 means 1 itself. But when it comes to the qubit, it is different based on the probability, based on the state of representation. So the value is whether it is the 0 value or 1 value, right? That is going to be changed. Suppose if it is 101 means 3-bit value, so we have the different states of 3-point representation. We have the different state representations, right? So we have the different gates are there, gate functions. How we are going to represent these gate functions, I will show you. So we have the Pauli X gate, Y and Z gate, right? So these gates, we are going to use these gates to represent the quantum to represent the quantum operators, right? So in the qubit, generally in the quantum computers, what we are saying is a basic variable is the qubit. So for
Preliminary, sir,
yes,
they are asking how to install
uh,
Qiskit.
yeah, I will tell you, sir, no problem. I will tell them. Okay, so uh, so here the simple thing is in quantum computers. So we have the qubit states. So for this we use the different so qubit representation. I think all you aware that in the last 4 days how we are representing using the different vectors and matrices form and with the complex numbers, right? So this is the basic thing of representing the qubit. Right. So now in our demonstration, we are going to see from the single qubit multiple and its Josa algorithm. Right. So so here we have the different operators are there. I think all you aware that is had mod and phase wise and C not gate. These are the different representations are there. I think all you are aware because just here I'm showing this format of representation because this format matrix format and matrix representation we cannot see in the Python Jupyter notebook. Directly we have this gate C not gate, CX and XY gates, those Pauli X gate and Y gate and Z gate. Directly I'll tell you this is the gate and how we are going to represent. Right. So these are the different gates we are going to see. And after these gates, now what we have to do is so we'll form the circuit. So now in the with the single bit representation, what is happening is will represents the only 1-bit representation, but what is happening is the true power of quantum computing is realized through the interaction between the qubits. So that's the purpose we are moving to the multiple qubits. So once we achieve this multiple qubits, so then we have to with these qubits and gates, we try to form the quantum circuit. So this quantum circuit is the computational routine consisting of the coherent quantum operations to perform the operations with the help of the qubits. Okay, so we have these qubits, and then we'll finally will see the quantum circuit. So for installing the Jupyter notebook is just pip3 install Jupyter, and in the similar fashion you can install. Yeah, I will show you here. Just a second. One second. Yeah. So for installing this QSKit, just you can type the pip install and QSKit. QSKit. Right. This is the command. Suppose you want to install this QSKit for doing the quantum computing. Just you type this command. Suppose if you are using the Python version, if you don't have the Jupyter notebook, so then you go to command prompt and there you can install this particular package. Right. So this is the one package, and the other one is the PyKill. But PyKill is some version is different. So you have to install from the starting onwards. First you install this Python upgraded version, and then it is not supporting for all the machines for the PyKill, but QSKit is supporting for all the environments. Okay, so I think all you are aware about the Jupyter. So once Jupyter is over, so then you can simply install the QSKit. So once this QSKit is installed. Just the thing is we have to import it. So the available, so why we have to import this particular thing is, so now all the predefined functionalities regarding to this quantum computer and quantum representation, the circuits and gates and bit representation, all the packages are written in this QSKit. So now we can just import this QSKit, right? From this QSKit, so your running is very simple in the Jupyter notebook. Just you take this any of the cell and you can run it. And suppose you want to insert any cell in between, just you can insert the cell. And you don't want some other cells, then simply you can cut these cells. It's a very simple thing, right? So this is a basic simple operation of the Python. I think you need not worry about this Jupyter notebook. It's like a simple English like language. Simply you can write, and whatever the command you can execute. It won't trouble you like a C and Java language. Let's simply suppose if I am now running this one, then my machine will become the slow, because that's the reason. Already we run these commands, and I keep here. At the end of the session, I will share this notebook with the conference, sorry, with the workshop chair, and they will send you this particular file, Jupyter notebook file. Right. So here the thing is, now first from the QSKit, I'm importing the quantum circuit. What is this quantum circuit? Suppose I want to represent any gate or to store the qubit or to create the qubit. So I required what? I required the quantum circuit. With the help of this quantum circuit only, we are going to create the qubit, right? So QC is equal to quantum circuit. Just I am creating a quantum circuit with one qubit. Once the quantum bit is created, now what I have to do now? I have to define the initial state. I have to initialize. I have to initialize my quantum bit. So initial state, what I'm saying, either it is 0, comma 1, QC dot initialize. QC dot initialize. What I'm initializing to the initial state. What is there in the initial state? I have the 0, comma 1, 0, comma 1, and I'm giving the 0 is the Q 0th bit. Right. So initialization, I am going to initializing my bit. And now just I want to draw this particular quantum circuit, QC dot draw. So just this is the function to view your circuit. So now how these circuits will be there means, yeah, I will show you. So these kind of circuits we are going to get in the future, right? So it shows the just QC dot draw. It will draws your it is simply how the value is going to be initialized, and the initialized value is going to be shown here, right? QC dot draw is going to be shown here. So now suppose now once this quantum bit is defined, suppose now I want to show this simulation. The simulation means whether how the states are initialized in between the 0 and 1 and in the complex representation. Right. So for this particular quantum circuit, so then we have to go for this particular. So here already I defined this functions: execute, AER, and plot the histogram for the visualization. For the mathematical operations, we have the I import from the math is the library, the sqrt and pi we have imported. All right. So backend, I want to represent the state vector simulator. We are using the AER for the backend. Right. Now I'm creating the quantum circuit, initialization the value, and result. I want to show the results. Execute the QC means what? Quantum bit. I represented in the backend. I want to show the result. Right now, in this case, what we are doing after creating the quantum circuit with one qubit, now applying the initialization operation to the 0th qubit. Right now, I want to show this with the simulator. Right. So the simulator is going to represent with the form of the state vector. The state vector we are representing in the complex numbers. So 0 plus 0j, comma 1 plus 0j. So the complex numbers mean we know in the max we represent a plus ib. Instead of high here we are representing the j. So this is the 0th bit, and this is the first bit representation in the complex number representation. right? So in the representation of these qubits, generally we'll use the 5 different instructions, right? One is the measure instruction. In the measure instruction, suppose for example, have the value like suppose I want to represent the value. If it is 002 beta and 01, next is 10 and 11. Suppose for the probability we have to give either sometimes what we are giving the probability of these values is we have to mention, suppose my outcome is 1 1, so then in this case the probability of this particular bit is 100%, right? The remaining all values are 0. So this one we are going to say uh, measure instruction. There are the 5 different instructions we are using: the measure instruction and hard mode instruction, phase, T gate, and C not gate. So these are the different forms of representations we are using, right? Yeah. So now, yeah, so just we want to measure all these particular values, whether the state is 0 or 1. We want to represent this particular one. So and this one we want to represent this, whether the value state, whether where the quantum beta. So how the probability is going to be measured, you want to know that particular thing. So we can use the count function, right? The results dot get counts is going to show the probabilities. So whether the value is in between the 0 0.255 and 0.7500. So where is the value? So I think in the qubit representation, all you are familiar that how the qubit is going to be represented in between the zeros and ones. So for that, the probabilities we are mentioning in between these values, the probability whether the value is 0 or 1, or what is the probability we are going to be represented, right? So this is how we are going to show with this particular value with the Instagram. And I think all you know the complex amplitude. So to define this complex values also, we can suppose in the previous case, just I initialize the vector is what initial state I represented with 0 comma 0, 0 comma 1. Now here what I'm representing is, suppose I want to represent complex amplitude. I want to represent in the initial state what I am taking 1 by square root of 2 comma 1j square root of 2. I want to take this complex representation of this qubit. So now you can take this one. Now you can take QC quantum circuit I define. Again I have to redefine, because why I have to redefine? Other earlier I defined the one quantum circuit. That's the reason again I'm creating the object. I'm QC, I'm redefining, and QC dot initialize. Now initial state is what with the complex amplitudes. We are using this complex amplitude, and again executing, and I'm representing this particular value, right? So here what is happening is the quantum circuit here. We redefine the quantum circuit, and with these particular corresponding values, now the value, just see here 0. How we are going to represent the complex format of the states of the qubit, 0 bit and 1 bit states, how we are going to be represent. Suppose you want to represent with the probabilities, so it is the zeros value and this is the 1 values with the histograms. With the histograms, how we can show these qubit values based on the probability variations. Okay, so now this is about the simple representation for the, this is with the simple representation 0 comma 1, and with the complex amplitudes we use the complex amplitudes also. So now the quantum circuit, just I want to draw this particular quantum circuit. So for the states of q0 and 1, how we are going to represent, right? So here in the previous case, now just you can see here. So when we draw this quantum circuit with the initialization of 0 1, so now this is the q0 0 and 1 initialized with 0 comma 1, and with this gate we are representing. But when it comes to this complex attribute, so now the what we are getting, the what is the weightage of these values we are getting here. So that value we are going to be representing QC dot draw. Right, the QC dot draw means is going to show that particular qubit QC dot measure all. So now we want to measure whether what is the value of this particular one. So with this gates we are going to be represent, right? So now after this, now we'll go to represent the single qubit gates. How we are going to represent this single qubit gates. Just now I already shown in the PPT the Pauli's gate, X gate, Y gate, and Z gate. So to represent these gates, it's very simple. So from Q gate, import star means suppose if I put the star means what, whatever the library functions are there, all the library functions I am using. Suppose if I'm not putting star, say if I want only specific function, so then what you have to do is you have to import that particular specific function only, that particular specific function only. Suppose you want more number of suppose you want why, what is the difference mentioning the specific name? Suppose now here you can see from math import pi I am using only pi, it is importing. In the math there are so many functions, tan, sine, cos are there, and I don't want all those things. Only I want the pi I'm using. So if I'm using like this, your system performance will be good. Suppose if I'm using the star means whether the libraries are required or not, even though we are going to import all the libraries, right? That is the problem with this particular star. So here what are the functions? Suppose here I'm using this all qubit gates, so that's why simply I put the a star, right? So now for the visualization, Q-skit visualization we are using plot, block, multi, vector. So now in the Fowley gate, so same thing. First thing is what you have to take now. You have to take QC, quantum circuit, for any to representation of the any qubit. So first, let's go with an X gate. X gate of the qubit. So now how to represent this Pauli X matrix means simply you can take quantum circuit QC dot X. QC dot X means you are going to show with the Pauli's X gate, right? Pauli's Anna, Pauli's X gate. So just we want to show with the X QC dot draw means. So now it is going to show the how we created this particular X gate. Suppose now I want to view this with the straight vector with this simulator view. So now how we are going to show with the multi-vector view. I think you know this is the 0 and 1. So this is a cubic, how we are going to represent this particular qubit in the multi-vector. So how the values, whether it's a 0 value or 1 value, how we suppose you want to show in this particular manner. So you can show using this backend this execute backend multi-vector view. So there you can plot this particular one. Suppose now you can combine. So now we can apply the Y and Z gates to our circuit. So now already what I already have QC dot X I already drawn. Now for this what I am doing QC dot Y. Now Y gate is the qubit 0. Bit what is the bit I'm adding? 0 only. Now QC dot Z. So now I'm adding the Z gate. Now QC dot draw. So already here we have taken the X gate, X gate. So now we are taking the X, Y and the Z gate. So three gates are going to be added. So you can draw this particular QC. So in the advanced gate, so suppose now the thing is I want to show more in detail about this, how we are measuring and how guaranteed to have the qubit in one end of these two states. So we can use the psychate allows the measure how we are going to use this Hadman gates, right? So to create this X measurement function, so simply we'll use the X measurement for the QC qubit. So simply the message is we are taking the CBIT is the message. Measure the qubit. So I want to measure the qubit. How we are measuring qubit? Measure the qubit CBIT. And so in the initial state, what is happening? I am taking the initial state is 0 comma 1. Quantum circuit, you are creating a quantum circuit with 1 comma 1 state initialize measurement. And so now in here what is happening is, so whenever we want to the Hadman gate, what is the Hadman gate it is saying is, so it takes the equal probability of the outcome. Suppose when I have the value is there, suppose now In the measure function, what I'm saying, the probability, if the outcome is 1 1, so the probability what I'm saying is 100%. But when it comes to the head mat gate, the percentage is it's a 25, and for this gate also it is 25 equal. The probability of the outcome of these all these circuits, what I'm saying is a 25%. All right, so this is the HUDMAT gate. What saying is, so the always the probability of occurring this particular event is equally. So the value of this particular event is 25%, 25%, and 25%. We are going to be represent like this. All right. So now this is the HUDMAT gate. We are going to initialize HMH. So this HUDMAT gate we are going to represent. So then we can represent the qubit, how we are going to view in the multi-vector of this particular qubit, right? And we can specify this OR gate also, OR gate with using the RZ, so pi and qubit. So how we are going to represent, how you want to take this particular quantum circuit. Again, you have to take qc dot rz pi 4 comma pi by 4. Pi means that pi 22 by 7 by 4. So now this is qc dot draw we are going to be representing. So this is the rz gate, and you want to add s gate. You want to s gate and sdg gate. So then simply you can take the quantum circuit, apply the s gate and sdg gate, and whenever you want to draw, you want to see this particular gates, so you can see this particular gates, and t gate also, T gate and TDG. So in the T gate and TDG gate. So how for everything you want to create anything. So first you take the quantum. You have to create the quantum circuit. So for that quantum circuit, whatever the gate you want to add, so you can add the QC dot T gate, QC dot TDG gate, and QC dot draw. So we are going to show this particular gates. Yeah, right. So we'll draw. These are the grids we are going to. These are the gates. So in the multiple qubits, suppose whenever we want to show this multiple qubits, the 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 libraries are similar only. So there is no change in the libraries. So now again we have to. So suppose now here quantum circuit. I'm taking the quantum circuit. How many? I'm taking the 3. Apply H gate to each qubit. Apply H gate to each qubit. So what we are doing, qubit in the range 3 means what? So I'm going to add the 3 qubits, QC dot H qubit. So what is this for loop mean? The for loop means in the range. Range is the what is the value 3. So up to this particular range, the values are going to be added. Right after this for loop completion only, I'm going to draw here. I hope you have some basic knowledge on these loops and the conditions in the Python. Yes, are you familiar?
Yes, sir.
Yeah, good. So you have the for loop. For loop is there. So in the for loop mean within the range. So in the why we are using the loops mean in the programming language. I want to repeat some particular task. I want to repeat some 5 times, 10 times, 100 times. So then we can use this one. So now we are adding. So within the range. Range is up to 3. I mentioned. So this up to 3. So these values are going to be added. Okay, so all these this notebook I will share with you. You can, after going home, you can execute it, no problem. It is simple only. You can, I given the command also. So those commands, just you install the Jupyter notebook and you work on one by one command, all the commands. Okay, so you guys can first. So the fundamental block is first you have to create the qubit, single gate, and then multiple gates. Once you know the creation of the multiple gates, then we can go for the circuits. Once the circuits we have drawn, then we can implement the algorithms. So today Grover's algorithm, Shore's algorithm, and Josh algorithm. So like that. So each algorithm of quantum computing is representing the one application. Some is for suppose Grover's algorithm as selection criteria, and now Josh algorithm is for to find whether it's a balanced or the constant function. So we have the different things are there. So if you want to implement those algorithms, you should know these fundamentals. Fundamentals mean from the bit level. So in the logic gates, I think in the logic gates in the computer design, you should know first bits, then and not or circuit gates. So then using that, you are going to build the half adder, full adder. So then different functionalities. Correct. In the similar fashion also here also. So right. So now in the quantum circuit, so we are representing this H gate and X gate. So we can qubit gates on the multi-qubit state vectors also we can create. We can create the number of state vectors. So in the qubit gates, suppose I want to represent the NOT gate, C NOT gate. So C naught gate means, so you can take the QC dot CX. So it is going to represent the C naught gate. Right. So once the implementation of these gates are completed, so now to solve, suppose what I told initially, so the quantum circuit, we want to represent this circuit. The quantum circuit is what? The computational routine. So we have it consists of the different quantum operations and the quantum data, right? Such as the qubits. So to do this particular thing, so we have to represent the quantum circuit. So we have the Dutch JOSA algorithm. So what is this algorithm is? This algorithm is having the built-in functionality. What is the algorithm? The main objective or the main I think this algorithm is covered in the theory portion. So briefly I will explain. So what this algorithm is doing is, so whether when we are working on a particular function or functionality, so whether the outcome of that particular functionality is a constant or the balanced one, balanced oracle. Oracle means is a problem statement. So the problem statement, what we are saying is, so when I run this particular algorithm, so the outcome is what, whether it is a constant or it is a balance. So for example, just here I will show you. Suppose now I'm representing f of x. I'm representing the f of x for these four states. These are for these four values. For example, 0, 0, 0, 1, 1, 0, 1, 1. Suppose if it is my oracle is constant. Constant mean my, what is my f of x value? F of 0 comma 0 is equal to f of 0 comma 0 comma 1 is equal to f of 1 comma 0, right, is equal to f of 1 comma 1. So for all, so whatever the input, the output is what? Constant. Always the output is constant, right? So this is the whether it is the constant. So in the balanced, what we are saying is, for this 0, 0 and 1, 1, the output is something, and for 0, 1 and for 1, 0, the output is different. Balance remains some 50%, the output is showing 0, and 50% the output is showing the 1. So the Dutch Josa algorithm, what it is saying is, for the given function or the given problem or the oracle, so the main aim is, we need to identify using the quantum bits, quantum circuits, whether the given thing is the constant or the balanced one. So the outcome of the function, always the outcome of the function is constant, or the outcome of the function is balanced. The outcome of the function is balanced. So for example, I think you know, so when you are at the kid, whatever you are asked, your father says no. Answer is what? Constant. Sometimes. So this example, it may not be the true. And balanced. Okay, sometimes they say yes and sometimes they say no. So in the similar fashion, suppose in any mathematical function, when you are doing any cryptography in the applications of quantum computing, so whether you are used for searching purpose, or there are different applications are there in the quantum computing. Especially we can use for the cyber security and financial modeling and the traffic optimization, for the weather forecasting. So why this, the beauty of this quantum computing is, the beauty of the quantum computing is it minimizes the computation compared to that classical computing. It minimizes the computing power, because instead of representing the classic bits, it is storing the one bit. Either at the time the value might be changes, right? So now, based on this principle, now the Dash-Josh algorithm is working, right? In this algorithm, so we have this Josh algorithm, Grover's and Shor's algorithms are there. So in this class, we'll see this Josh algorithm, and the next class we'll see the Grover's and Shor's algorithm. All right. So here, there are so many inbuilt functionalities are there for solving this, because the mathematical notation of this algorithm is very difficult. So the representations are very complex notations are there. So all those notations they have given with using these import functionalities, right? So for all those things we read the qskit only. So don't confuse. This NumPy is the basic mathematic Python library. NumPy and Pandas are the basic Python libraries. So there are so many libraries are there in the Python. So, but for all our quantum computing purpose, so we use the qskit only. Right? This NumPy is the just for the to represent the array and such kind of things. Only we can use this NumPy as NP. Right? So we have the NumPy is there, and then we will use these are the different libraries from the IBM and Basic Air and least busy quantum circuit and execute. These are all things we have seen already. So now the length of the bit input string, how much I'm taking, n is equal to 3. Length of the bit means either it is 00, or I think 001. 3-bit representation means 010 and space 100 and 101, like this. I think this 3-bit representation. So here we are taking the values, we are initializing the length of the n bit input string is 3. So if it is balanced, mean what? For all the inputs, whether I'm giving 00 or 001 or 101 or whatever the value, if I'm giving, the output is constant. So to define that, we have to define the constant oracle and balanced oracle. So we are now what we are doing, we are implementing the algorithm. We are implementing the algorithm for what? We are implementing the algorithm for the Josh algorithm, right? For this we have to define the constant oracle. So in the constant oracle, what we are taking, first I am defining the quantum circuit with n plus 1. So here we have the n is the input states are there, and we'll get the total 2 to the power n plus 1, 2 to the power n plus 1 states we are going to get, and we have to define. So random is the one function in the max. We have the random number, random entity is generating in the Python, right? So always the output is equal to 1 constant oracle, because what I told in the constant oracle means always will get the constant output only, the constant output, whether the bit is 0, 1, 2, 3, right? So we are going to get the output 1. For the balanced oracle, so now how we are going to define this balanced oracle? So now qubit in the range. Why I'm saying for the balanced thing, we have to do it. If b of string is equal to 1, so balanced oracle. Otherwise, else part balanced oracle. Right? We have the two things. When it is equal to 1, it is going to be happen. Otherwise, 0. There are the chances of the twos are there. Right? So this balanced oracle we are writing. So now for this, we have to define our own the functionality for the balanced oracle with the qubit. So now qubit size, how much I'm taking, the qubit size is the 3, and the length of, so just see here, this is a mathematical function qubit in the range. Range means how many bits I have took? 3 bits. N value is the 3 bits, either 000 or 001 or 101 or 11 like that. So the for loop, what it is saying, within the range, I have to perform these operations. Each bit, whether it is equal to 0 or 1, we have to identify. So use the barrier. So once whether it's a balanced oracle or not, we have to identify. Right. So in the same thing, controlled not gates in the range. Again, if it is not there, so then you have to add. CX means not gate, controlled not gate. I'm going to be add this controlled not gate. So this balanced oracle barrier and balanced oracle draw. So here we are drawing this particular one, how the gates we are going to be represented when the bit is 0, and in these two positions the output we are going to get, right, either for the 0 0 or 0 1. Right, in the balanced oracle also same thing we have to write, whether we have to compare with the string within the qubit string, we have to take the qubit, and with the for loop within the range.
Sir,
Yes.
sir, I had a doubt in the last thing you said, the constant oracle, right, sir?
Yes,
In
madam.
that, which bit qubit we are referring it as output, sir? Output is obtained from the previous cell, the above one, above this constant oracle, sir. Here, all 4 qubits give me the answer. No, sir, not this one. Just above.
Yeah.
Here,
Right,
here.
yeah.
Which
Constant.
qubit gives me the output, sir? Whether it
But
is all 4 or
any qubit you will get the only one answer, madam. Constant mean without the input.
that
So
is
for
0 into q0.
yeah, whatever the input we are giving. So have you haven't gone through the theory part of this particular algorithm, madam?
No, I have gone through, but how to measure the output is something that I'm not very sure of, sir.
Yes, madam. So here the simple thing is what we are taking is the length is 3 we are taking here for the output in any bit whatever we are getting. So output is what? 1. We are constantly we are representing what? 1 only, because whatever the input. So here for the 0001 or 1011, for all the 4 states we'll draw the output is the constant. We are not bothered about the whatever the input we are going to get. Right, so that's the reason we are representing with the, for all the values we'll get the constant output only. But when comes to the balanced, we have to check whether the bit is 1 or 0. Based on that only we have to add the value. We have to add that particular value to that particular gate. Based on that we are going to get the balanced one. Is it clear, madam?
Yes, sir. Yes, sir.
Yeah. So we are representing the constant and balanced, right? So once this part, so all these things are we have to define how we are going to represent the bits, qubits for the balanced as well as the constant gates. Once this is over, now the algorithm, how we are going to work this particular algorithm is, so we have to define the quantum circuit and give the numbers within the qubit range. We have to define these numbers, and we have to supply these numbers to this particular one. So now here let's apply the oracle. So for both as well as balanced oracle, what we created in the above, and this is for the constant, right? For both the algorithms, the functionality. So now here, what the functionalities we defined. This is the I think all you are aware about the functions, general functions of representing the functions. Suppose now here, just here, import numpy as np like this. This is the built-in functionalities are available. Now what we are doing is we are defining our own functionalities. Our own functionalities. Our own functionalities mean whenever we want to perform some operation repeatedly for that particular task, we can define our own functionalities. Right, that functionalities we have to call the previous values. So like this. So here, yeah, one functionality. Yeah. So this is the functionality. We have to define means. So we have to define DJ oracle. So now in this, whatever the things we created in the above, we are calling one by one functional. This is the complete algorithm of Dutch Josha algorithm. So once we implemented this algorithm, the final state we are going to get for the n is equal to 4, we'll get the output like this. And the probability of the density probability values of this particular value is going to be given along with the probabilities. We can draw the histograms for the given circuit. So the functionality is somewhat critical. So you have to define. This is the defining means we are defining our own functionality. Not this is not the built-in. So there is no direct built-in functionalities are not there for any of the quantum computing algorithms. Suppose in the machine learning and deep learning algorithms, so directly we have the algorithms are there. Algorithms means suppose I want to implement a support vector machine, directly I can use the SVM. But in the Python, it's in the quantum computing, it's not there, right? That's the reason. So we wrote a huge, more than 100 lines of code, more than 100 lines of code. So you step by step you evaluate mathematically and trace the functionality. Then only you are able to trace this particular algorithm. Okay. So anyhow, I will share this code with our faculty, and they will they will share you. And there is a separate textbook is there for doing all these things. We have the qubit, and other one is PyKill is also there. I told you na PyKill. So PyKill also one library is there. So in this also you can use this PyKill. There are lots of codes are already designed in the stored in the GitHub. From there you can get it. And other one is the QScatter. We have the QScatter separate book is there. So from this also you can learn. QSet.org textbook is there. There they defined all the algorithms from the scratch. Okay, and this QSkit is a I think PyKill is not working in all the Python environments, but this QSkit is working in all the environments. Mean whether you're using the Linux or Windows, any version of the Windows also, it is working. Any version of the Windows also, this QSkit is working. But PyKill is not working in all the environments. Just you can try whether whichever is comfortable, you feel comfortable, then you can use it. Okay. Yeah. Any doubts? Suresh sir.
One query they have, sir.
What sir?
Praveen sir asking
In
something.
chat box, huh?
Yes, sir.
Okay. Excuse me for a complete question now that I am running QC algorithm on classic machine. QC.
Is it that QC
I was initially of the impression that it is something that yes to CUDA for GPU written for the specific hardware. Yes, sir. Some of the packages are specifically designed for the GPU and CUDA, so only we can run on those machines. But qubit is working on this particular one. It's not required. Suppose you want to run that kind of thing, so then you better use the Google Colab notebook. So there you can work on those particular things. Google Colab is the freely providing. So there you can run these kind of algorithms. You need not GPU, and you know not the Hadoop or CUDA architecture for your to run that algorithm. Just if you have the Gmail, in the Gmail directly here I will show you. Yeah, just 1 second, sir. Here, just you go to this one. Here, Google Colab is there. Yeah, yeah. Google Collaborator is there. So this one. So just you can click and you can use the GPUs directly. You need not to buy the GPU or any other hardware requirements. In the Google Collaborator, you will get. They are going to give 8 GB or 16 GB, 64, whatever the size you want. Even TPU also they are providing. Yes, sir. Definitely we can quantify the performance. Sorry, chatting. Any more questions? So in the tomorrow, we will show you the grows and shows algorithm. So those two algorithms we will show you in the tomorrow session. In the meanwhile, just you can practice this QSkit, how you to use and how you are to creating and how you are representing these qubits. And you try to install Jupyter Notebook. Jupyter Notebook also very simple. Just you can type here Python or Jupyter Notebook. So then directly you can install from the Google and you can practice it. It's the simple one. You need not worry. So directly you can install it and you can use practice all these commands today at home. Okay.
Okay, sir. Mamta madam?
Thank you, sir. Thank you.
Wait, sir. Mamta madam.
I-
Mamta madam?
Sir, yes. My mic was troubling. Yes, sir.
Yeah.
Hello.
Sir, madam, sir, session is completed. Over.
Okay, yeah. Shall we go ahead with the? We have also with there was a chat. I was thinking to ask at it. Anyhow, the ma'am asked the question, and you also helped sir to read out those chats.
Yes,
Sorry,
yes,
ma'am.
madam.
Yes. We'll go ahead with the vote of thanks.
Yes, madam.
Yeah, on behalf of CBIT and the participants and all the people over here, the organizers and the co-coordinating colleague of yours, I thank you for this wonderful presentation, sir. Hope everyone might have learned the things and had a very good hands-on session of this. Thank you, sir.
Thank you, sir. Thank you, ma'am.
Thank you, ma'am. Thank you, sir.
Thank you, Ravindra sir.
Thank you, sir.
Yeah, thank you. Thank you.
Thank you, Ravindra Reddy sir.
Okay, sir. Thank you, sir. Thank you.
Then
I request all the participants to join tomorrow for the last day of the FDP.
and tomorrow there will be exam quiz. Everyone should score more than 60 marks to get a certificate, and everyone should attempt the test quiz. Okay, na madam? Madam, Mamta madam.
Yes, sir.
Yeah.
Yeah. Shall we
Okay,
close
madam?
the sessions? Yes, sir.
Shall we leave the madam?
Yes, sir. Hope we don't have any queries also. All the questions have been answered and hope things are okay. Yes. Thank you all the participants for all your active participation. Thank you one and all.